Let's consider finding the center of mass of some shapes. We'll have a couple here that aren't too difficult. These kind of problems show up on AP tests. They're good multiple choice questions, by the way. So we have two wires of length L, and you can consider the diameter of the wires to be really thin. So they're basically infinitesimally thin. So we don't have to worry about the spatial extent of the wire itself. But they do have mass. And the way this is, you see a little triangle here. There is symmetry along the vertical axis. Now, the center mass always lies along a line of symmetry. So somewhere along this line of symmetry is the center mass. The question is where? Well, this is really quite simple. Halfway up, because the center mass of each one of these wires of length L is right in the center, right there. The other one is right there. And since it lies along this axis, it's just going to be a line that crosses through there. That is the location of the center mass. You can think of it as one half of the way up. We could do the math here. 1/2 of L cosine of phi over 2. So here's phi. Phi over 2, you think of this right triangle. 1/2 of L times cosine. So it's halfway from here up, from the apex to that point, or from a line from the bottom to that point. Both would give you the same thing. How about this one? Now we have 3 chunks of wire, all of length L. And let's put the coordinate system judiciously right here, because we recognize that X position of the center mass, since these two are the same, and this wire along the bottom, the center mass of it is right there. There's symmetry along this axis here, and that's therefore the location of the center mass in the X direction, L over 2. Making the reference here at X is equal to 0. Now, Y center mass, you may be able to figure it out in your head, but be careful. We can put it into the center mass equation, and we have to account for each of the 3. So this M, from this location here, Y is equal to 0, L over 2, the center mass is here. And the second one, the center mass is right there in the center. And from this being the reference point, the center mass of this bottom one has 0 spatial extent, so M times 0. All over the total mass, which is 3M, masses go away and we get L over 3 from the bottom. So that locates the position of the center mass right there. Let's try a couple more of these since they're so much fun. Here's a couple wires, and we have one along the X direction, one along the Y direction. Both length L, to make it easy. Position of the center of mass in the X. Well, if it was just this one, it'd be right there in the center. Center mass of this one in the X is right there at 0. So we can plug in M times 0 plus this M times L over 2 divided by 2M. Gives us L over 4. So there's the center mass in the X direction, L over 4, and for similar reasons, Y center mass is going to be the same thing. And therefore we can uniquely specify the center of mass right there. Now let's try this one. So we have a isosceles triangle. We have our frame of reference. X will be along the bottom there. X center mass, there is symmetry here. You can see the line of symmetry running it right down the center. So that's going to locate somewhere along this line the center mass. And you might think, oh, it's right in the center, isn't it? Well, yeah, it is. Let's kind of look at how we'd find the center mass in the Y. So from the bottom, we have each one of these masses has a center mass right there. So that's L over 2 times the height. So the height is L over 2 sine of this angle. Okay, that'll give us the elevation to the center mass of each one of these. And this one over here. So that's M L over 2 sine of 60 for both of those. Obviously 0 for this in the Y direction. over 3 times the mass, which is L over 3 sine of 60. Well, it was pretty easy to find the center of mass for a system of particles. And we extended that to finding the center of mass at the geometric center. Actually, we didn't find it. We basically assumed that the center of mass for a uniform wire, for instance, was at the geometric center. And we used that to find the center of mass of a system of those wires. Well, we haven't demonstrated that the center mass for a long uniform wire is truly at the geometric center. So let's do that. Recognizing that the center mass in a given dimension is the sum of the positions of the particles times the mass of the particles divided by the entire mass of the system. Well, to do this perfectly, we're going to have to integrate all those particle positions times the differential masses divided by the total mass, which is m. So it'd be 1 over m times the integral, adding up all the positions times the differential masses. So that has the form that we want for center of mass. Same thing in the y direction. So let's put our rod of uniform density along the x-axis, mass m. Let's note also that density is mass over volume. We'll come back to that in a little bit. Density is mass over volume. But what we need to do here is integrate along the x-axis, and we're not going to worry about y because this is a one-dimensional object. But we need to integrate with respect to dx, not dm. So we have this formula in terms of dm. But how do you do that? Quantitatively, it'd be very difficult to know how to do that. So how are we going to integrate with respect to dx? We're going to convert the dm to dx. Not a problem. Recognizing that differential mass is m over L dx. Now, if that confuses you a little bit, recognize that mass per length, okay, so total mass over the length, is a kilograms over meters, and you're multiplied by differential x, which is meters, so you get kilograms equals kilograms. So mass per length times length, right? Mass per length times length is obviously mass, but because it's differential length, it becomes differential mass. So differential mass is differential mass. Is that all perfectly clear? Well, I hope so. Now, x center of mass then is 1 over m integral of x. Instead of dm, we're going to go m over L dx. Of course, the m's go away, and we get 1 over L integral from 0 to L. Those are the limits of the integration of x dx. Well, that's really easy to solve. 1 over L x squared over 2 from 0 to L gives us L over 2. And yes, that's in fact exactly what we assumed it to be. Indeed, the center of mass is in the geometric center for a long uniform rod. Since we had so much fun deriving the result that the center of mass for a uniform rod is at its geometric center, let's do it again, but this time you're not going to be able to relax so much. You're going to have to focus a little bit because we're going to change the density along the length. This is going to be a little bit more intricate. So here's our general format for finding the position of the center masses. 1 over m integral of x dm, etc. So this time the rod along the x-axis has mass m as before, but the density changes as denoted by the changing color. All right, so as it gets darker, it's more dense. So the density is literally proportional to the position x. So that should be interesting. Now we have to convert dm to dx because we can't deal with dm directly. Realizing that the mass is density times volume and density changes, we're going to utilize that idea and let dm be alpha x, which is density, times the differential volume, alpha dx. I'm sorry, A dx, cross-sectional area A, times dx. So dm is rho dv. Goes back to this. Mass is density times volume, so differential mass is density times differential volume. That's all we're saying here. So dm is rho dv, which is alpha x times a dx. Now we have to find the mass of the entire rod in terms of those quantities. So all mass is going to be, of course, is the sum of all the dm's. So let's integrate dm to get m. Well, to integrate dm, we bring out the constants, which is alpha, and a are the constants. Integral of x dx. So there it is, from 0 to L. And that's just alpha a L squared over 2. Now we want to find the position of the center of mass. We go 1 over m integral of x dm. Well, we just solved for m. We just solved for m by integrating dm. We got this, alpha a L squared over 2. So 1 over m is simply the inverse of that, 2 over alpha a L squared. Of course, those are all constants, so that's really nice. They're characteristics of the problem. So the integral of x dm from 0 to L is x dm. We already solved for dm, alpha x a dx. So that's pretty expansive, but very happily, alphas cancel, the a's cancel, and the x's will combine here in the integrand. So we have 2 over L squared, integral from 0 to L, x squared dx. And that's pretty easy to solve. Gives us 2 over L squared, x a third over 3 from 0 to L, and finally 2/3 L is the location of the center of mass for such a rod of increasing density. So there it is at 2/3 of the length of the entire rod. Wasn't that a lot of fun? I hope you agree.